Hey folks, how we doing? I'm back here at the house recording more lectures. Hope you're settling in and doing well. I'm wearing a Hawaiian shirt. I got reggae on. Hopefully this makes things a little more chill and happy today for you. All right, let's get it going with this lecture. So let me just walk you through what we're going to be doing. So we're moving into this new chapter, chapter 13 on chemical kinetics. And this is actually one of my favorite subjects. This is where I do research. This is what I do in my lab. And so I'll try to point out certain things that I do, and you might have some interest in that. I also have students that work in my lab, of course, when we can have people in the lab doing experimental kinetics. So kinetics deals with the time aspect of chemistry. It deals with how fast chemistry happens, or the rate of a reaction, as you can see right here, reaction rate. And so I've got a couple examples up here, and let's just talk about this reaction. So this is the reaction of N2 with O2 to make 2NO. And an important thing to establish here in this chemical kinetics, and this might be kind of obvious, but still we're going to start from the beginning. Okay, so reactants disappear, and so sometimes we call that decay. So their concentration decays over time. And products appear. So products evolve over time. Okay? So that might sound kind of obvious, but we're going to use this language a lot. Reactants decay, products evolve. And now, if you've taken calculus, you might be looking at some of the stuff that I've got on the slide here, and you might be thinking, oh yeah, this is a great use of calculus, and it is. And in my upper division course, Chem 361, PChem, we actually go through chemical kinetics using calculus. Calculus is not a requirement of this course, so we're going to do this, we're going to kind of skirt around the calculus stuff. So if we were to look at the rate of NO formation or NO evolution, and if we were to compare that to the rate of N2 consumption and O2 consumption, or O2 and N2 decay, right? We have this delta NO over delta T, okay? And recall the brackets still mean concentration in molarity, okay? So we're still dealing with brackets here. And then now this delta T is related to the change in time, okay? And so you can see there's deltas there, and remember that delta is final minus initial. So we know that the NO formation is going to have a positive rate because it's appearing. However, the N2 consumption and the O2 consumption, or the O2 rate and the N2 rate, those are going to have negative rates because they are disappearing, okay? So that's important to note here. And sometimes we will also often deal with the absolute value of these rates, but we should recognize that a reactant is going to have a negative rate of consumption, and a product is going to have a positive rate of formation. Okay, so and we can relate these things to each other via stoichiometry, and we call that the relative rates. Okay, so I'll still keep this reaction written here on the board. And so what the relative rate gives us is it's a way of relating all of these various rates to each chemical species in the reaction. And it's important to note, if we were talking about the absolute rates, they will all have different absolute rates, but they will all have the same relative rate when we apply this formula right here, okay? So we can see in the stoichiometry, N2 and O2 are 1 to 1. So that means their rate is equal, right? The rate of consumption of N2 is going to be equal to the rate of consumption of O2 because they're a 1-to-1 stoichiometry. But now this is where this gets a little tricky. And if we want to think of how this relates to NO formation, for every one N2 and one O2 that are consumed, two NOs are created. So what that means is the absolute rate of NO formation is actually 2 times greater than the absolute rate of O2 and N2 consumption. Because remember, for every one N2 and one O2 we consume, we make 2 NOs. So that means if we want to relate these things to each other in a relative way, so we get all these rates equal to each other, the NO rate is going to be positive, okay? And it's going to have to be 1/2 of that value. So I put that 2 over there. I'll bring that out to the side, and we'll say that's times 1/2. Okay. Another thing to note, you might be saying, well, how does a negative and a negative equal a positive? Well, remember, this is going to be the N2 final minus the N2 initial, for example, over T final minus T initial. Well, if N2 gets completely consumed, then this value is going to be 0. And so whatever the initial value is, let's suppose it was 1 molar. If that's 1 molar, then 0 minus 1 is a negative, and a negative times a negative makes a positive. So that's why all of these rates will in fact actually be equal to each other. Okay? And so if we wanted to think of this generically here, okay, I'll rewrite the equation generically. And actually, no, let's go ahead and leave this on, and I'll go to the next slide, and then we'll talk about the generic equation. Okay, so let's switch slides here. So now if we look graphically at what's going on here, okay, so on this graph right here, on the y-axis is the concentration, and that's in micromolar. Don't worry about the micro, right? It's still molarity, okay? And then on the x-axis, it's time in microseconds. So this is a really fast reaction at really low concentration. But in any event, our time unit, I didn't say this before, but our time unit is almost always in seconds, but it doesn't have to be. It can be in hours, minutes, days, years, nanoseconds, whatever is appropriate for the reaction. If it's a very fast reaction, using a small unit like a microsecond is logical. But if it's a very slow reaction, then using something like years for your time would make more sense. Okay. So now if we look here at this blue curve describes the decay of N2 and O2, and you can see it's a negative rate. It's a negative slope. And so remember, slope, we'll write that down, is rise over run. And it's really like the change in the rise over the change in the run, right? Which basically means delta y over delta x. So that's why if we have this plotted as concentration on y and time versus x, our slope is going to give us our reaction rate, okay? And there's going to be a couple different ways we talk about slopes. For those of you that are good at math, you might recognize, well, this slope is not constant over the whole reaction. And that's true, and we're going to talk about how to deal with that. And we notice here that N2 and O2, they're on the same curve because if they both started at the same initial concentration, they have the same stoichiometry, right? The rates are both negative delta N2 over delta T and negative delta O2 over delta T. So they have the same rate. But now you look at the NO rate, and what's plotted on here, these graphs are the absolute rates, okay? On this graph here, let me redraw this actually so I can annotate it. All right, so here is my decay of reactants, and then my evolution of products is actually twice as high, right? So if I looked at like a slope, let's say like at this data point right here, so this slope is actually 2 times the slope of the reactants, okay? So here on this graph, we're actually seeing the absolute rates. And so the way that we can make those all equal, the way we can make them relative to each other is, again, with that stoichiometry, is saying 1 over that 2 coefficient. Okay, so now let's look at a way to do this generically for any reaction. If I write, let's say, lowercase a and big A plus lowercase b and big B reacts to form C and D, where my lowercase letters are my stoichiometric coefficients, however I balance the reaction, and the uppercase letters are my chemical symbols, then I can relate my rates to each other by the following. Negative 1 over lowercase a, and then delta A over delta T, and that's going to equal negative 1 over lowercase b, delta B, delta T, and that, of course, equals positive 1 over lowercase c times delta C over delta T, which equals positive 1 over lowercase d times delta D over delta T. Okay. So no matter what any of those coefficients were, if you recognize this is how we can do this equation generically, then balance the reaction and then just go for it. Okay, so I'm going to give you an example problem to work on. Let me switch it up here. So here is our synthesis of ammonia from nitrogen and hydrogen. So write the relative rate of each reactant and product. And here it says relative to N2. Okay, so that means we can keep this balanced with a 1 is basically what that means. And I'm going to play a little bit of music while I work through this problem. You can, of course, pause the video if you want. But this should be pretty short, so I'll go ahead and work through it now. All right. Okay, so that wasn't so bad, right? So I just kind of followed through this generic example here. And by saying relative to N2, again, that all just means we're just keeping a 1, a coefficient of 1 right in front. And now we can see that the hydrogen rate is 1/3 the nitrogen rate, or really, excuse me, I should say, the hydrogen rate is actually 3 times the nitrogen rate. And the ammonia rate would actually be 2 times the hydrogen rate. And we could even relate how the hydrogen and the ammonia relate to each other, for example, by doing the following. I could say negative 2/3 delta H2 over delta T equals positive delta NH3 delta T. And then now I could say that the hydrogen rate is 3/2 that of the ammonia rate, or I could say the ammonia rate is 2/3 of the hydrogen rate, right? It depends on which one you've got a coefficient of 1. And of course, if we looked at how those rates relate to each other, so if I draw what the nitrogen looks like, so suppose we're all starting up here with my reactants, my nitrogen would look something like this, okay? And my hydrogen would be 3 times greater, right? So it would have a much steeper slope, something like that. And my ammonia would be, 2/3 of the hydrogen, or I could say my ammonia is 2 times that of nitrogen. And, if I drew that, it would be something like this. Pretend I know how to draw things exactly with those proportions, okay? And so, for example, if let's say we analyzed maybe the slope of the hydrogen case, okay? And suppose that we found that was 0.5 molar per second. I'm just saying, suppose the hydrogen was 0.5 molar per second, all right? Then easily I could substitute any place that I see delta H2 over delta T, I could substitute 0.5 molar per second, and then that would actually give me what the nitrogen rate is, that would give me what the ammonia rate is, and of course I'd have to do that algebra to figure it out. For example, suppose I wanted to know, based on what the hydrogen rate is, suppose I wanted to know what the ammonia rate is. So I could say negative 2/3 times, and of course, excuse me, that's a negative rate there, so a negative negative makes a positive. So and then of course it would be negative 2/3 times negative 0.5. Let's just do that in the calculator real quick. Right, so that's 1/3. So then that means the nitrogen rate would be positive 0.33 molar per second, and it's absolute rate. Okay. Okay, so I'm going to move on past from relative reaction rates, but before I do that, I'm going to switch over here to one of these learning goals. So here we go, 13, learning goal 1, understand how reaction rates relate to the change in concentration of reactants or products over time, and be able to write the relative rate of each species. So that was just learning goal number 1 right there. Okay. So make sure you understand that first learning goal. I'm going to move to the second learning goal right here. Understand the difference between average rate, instantaneous rate, and initial rate. So once again, what we've talked about so far are relative rates and absolute rates. Okay, so now let's move forward here. Okay, great. So moving on. So now, if I go back, I'm going to keep drawing here various graphs. I'm just going to put a big one up here where we have now concentration and molarity, right, versus time, and we know that that could be in seconds, minutes, hours, days, whatever, right? So now if I look at this, I'll do a reactant slope right here, or reactant rate, and we'll do a product rate. Okay, so now there's a couple different ways that we can calculate all of these rates. And as it turns out, none of them are really that great, and you'll see why in a moment. So our average rate, this is one of the types of rates that we're going to discuss. And there's going to be, I think, 5 in total. Relative, absolute, which we've already talked about, average, instantaneous, and then initial. So that's 5. So we've done 2 so far, relative and absolute. Now let's talk about average rate. So average rate is the change in concentration of a reactant over product over a specific time interval. So exactly what this picture is showing you, if I have a data point, here and then here for my product, okay, then I know that this was my change in concentration, and this, so that's change in a C, let's say for concentration, and this is my change in time. And so that would give me the average rate that's occurring over this interval. And of course, if that was a straight line, if let's say that was a straight slope, then the average rate would do a really good job. And in some cases, this will be a straight line. So we'll talk later about what gives these reaction profiles their curvature. Sometimes they have this kind of exponential decay like you're seeing now, but sometimes they don't. So in any event, this average rate, if I knew this data point and this data point, the times and the concentrations, then I could calculate the average rate. But if there's curvature over this interval, the average rate is not going to be very meaningful. Okay? So let's switch it up now. And another type of rate we could talk about would be the instantaneous. Okay? And instead of doing the instantaneous, if I was able to do calculus, and let's say I identified a point, so let's suppose now over my same interval, maybe I take the point that's like halfway between, and I was able to do calculus on this thing, so I took the first derivative, right, which would give me the tangential slope at that point, then that would give me the instantaneous rate. Okay, and I could do that, at this data point, and I could also do that at this data point for the reactants, to compare the two slopes. But now what you notice, what you might see here, if I was doing the instantaneous rate at this data point compared to maybe this data point, right? This would be my instantaneous rate for the products here, and this would be my instantaneous rate for the reactants here. You notice that my, so if let's say this is number 1 and this is number 2, my instantaneous rates for number 1 and number 2 are going to be different. And so I'm going to have to specify at what time is this an instantaneous rate. And so what we do, if instantaneous rate is to be used, then what we do is actually use the instantaneous initial rate. Okay, so let me erase all this again here. So the initial rate, right, this is the 5th thing that I mentioned. The instantaneous rate is still, excuse me, the initial rate is still the instantaneous rate. However, it is at the very beginning of the experiment. So my products, excuse me, my reactants, my products. And so now the initial rate would be, if I look at this very first data point at, of course, t equals 0, at time equals 0, then I would have an initial instantaneous rate here, and I would have an initial instantaneous rate here. And now, even though that wouldn't be comparable if I look at later on in the reaction time, you know what I mean? If I compare those initial rates to like rates out here, they're still going to be different. However, if we are going to use instantaneous rate, it is preferred to use the initial rate. Okay? And the last thing I'm going to say, this is a relatively short video for this very first one. So I'm going to do 4 kinetics videos, okay, because this is a bigger section. And then the last thing that I'll say, just briefly on reversible reactions, okay? When we do have an equilibrium reaction, the reversible reaction is important, but only when the products have had time to build. So like out into this point, okay? And that's why we like to choose the initial rate, because at the initial rate, the reverse reaction hasn't had a whole lot of time to proceed. And also, let me extend these a little bit. If you remember from your equilibrium, and don't forget equilibrium, right? At least with this particular reaction that I've been highlighting, okay, we can actually see that it's going to have equilibrium, because if you remember, equilibrium occurs when the concentrations stop changing, right? So if I looked at the rate at these points, you know, the rates are equal to 0. So equilibrium is occurring right here, okay? And so then the reverse reaction is actually fairly important at that point. So that's why when we're studying kinetics and we're trying to quantify or calculate reaction rates, we like the instantaneous initial rate. All the same, it's still not totally accurate when we want to compare across the whole time sequence. So in the next lesson, in the next lecture, I'm going to introduce a new concept that gets us around all of these, you know, relative rates, absolute rates, average rates, instantaneous rates, and initial rates. What we really want is a rate constant that will be constant across the whole reaction time. Okay, and that's what I'm going to introduce next in our next video lecture. All right, so let's see, and then the last thing I'll say here, yes, so understand the difference between average rate, instantaneous rate, and initial rate. Okay, so this is a nice short and sweet video. We just did 2 learning goals. Make sure you're okay with this one, because now in the next videos I'm going to move on, and it will get a little bit more complicated. So again, make sure you understand these simple concepts before we move on to the more complicated concepts. All right, folks, I'll see you in the next video.